Hello and good morning everyone, welcome back to our channel, and let's continue with the very informative tutorial on CNC programming. Let's start by looking at the extremely interesting part of turning, which in my opinion are the variables. All of you. Using variables allows the program to take on different aspects while keeping the same programming. First of all, what do we mean by variables? So we always think of x and z as numbers. And as I mentioned earlier, x and z are indeed numbers, but they are mainly values. Values that can be changed beforehand. That is, before programming x and z with variables. Let's try to think of something very, very simple. I need to perform the turning of bars. So we have a bar clamped in the jaws and on the tailstock. This is, in essence, our axis of rotation for the piece. And here we have essentially our 0 point, specifically, as it were, in this context. We need to work on these bars of equal length, but with different diameters, because we have a bar that's 100 long, a bar with a diameter of 100, and a bar with a diameter of 105. Let's say we set up a program for a part with a diameter of 100 and a length of 400. In short, we position the tool here, we turn it for 400 in length, removing material to ensure that the final diameter achieved is 100. That's what we're doing. A percentage program from 0 to 100. Put in data G92, S2000, M42, G95, T0, 1. G95, T0, 1. G0, Z0, actually, Z10, X100, G1, Z400, F03, G0, X200, Z100, M5, M30. It's a basic and simple program that basically tells my tool to go to 10 millimeters at the face of a piece with a diameter of 100, turning for a length of 400 millimeters at a feed rate of FE03, and then it tells me to move away. Now, in this particular case, I find myself in a situation where I have approximately 200 bars in front of me right now. But out of these 200 specifically, I need to make 10 with a diameter of 100, 4 with a diameter of 150, 5 with a diameter of 100.7, and so on, all fortunately for a length of 400 respectively. In this specific instance, as a result, in this scenario, in this context, to be precise, in total, regardless of the inconvenience, regardless of the fact that we can copy the program and manipulate it as many times as we want, regardless of the fact that this is just data, we could do something like this. If I left a space, it was better. G95T0. Insert a variable here, and indeed simply say A equals 100 for the diameter, and indeed indicate X, not as a numerical value, but as a letter, specifically the letter A. Change to 105. X becomes 105. In simple programs, this style is limited. Changing a program takes as long as changing X100, X105, X130. The goal is to use variables as letters, not code. Of course, with such a simple program, the usefulness of this type of programming is quite limited, because it takes me just as long to change a program as it does to change X100, X105, X130. and it actually takes me longer to modify the clamps. But that's the point, to insert variables, in the form of letters rather than codes. For example, Fanuc indicates variable. Hashtag 101, hashtag 102, and so forth and so on, and then you match them to numerical values, and our program takes on different characteristics based on the variables I put in the program text or modify during the program execution. For the sake of convenience, we'll just refer to the variables as letters. Variables can be used as both values and logical operators, which means mathematical operations. For instance, a can equal 5, and during the program I can write a is equal to a plus 2, and therefore a will become 7. I can have two variables, a and b, both equal to 3, and midway through the program I can say a or c equals a plus b. I can have variables such as a equals b divided by c, or b equals b times c, which means that b gets multiplied by c, and subsequently in the next line it will be read as a different value. Therefore, we're focusing on mathematical operators today, specifically the ability to pair variables with our coordinates. A simple example: I have a family of pieces like this, where I have constants like R5, unquoted fillets equal to 2 times 45. And they change. The diameters and lengths. I can create a program that very simply, instead of X and Z, so what do I do? At the beginning of the program, I need to identify these variables, which are crucial for the subsequent steps and ensure the program runs smoothly. So A equals D1, which is the first dimension, B equals D2, the second dimension, C equals D3, the third dimension, D equals L1, the first length, and E equals L2, the second length. These variables are foundational to our calculations and operations. Now, I would need a multi-page whiteboard to effectively map out and visualize the entire process, allowing us to see the bigger picture and make necessary adjustments. So let's say we do it like we did at the beginning of our tutorial, where we laid out each step in detail, ensuring clarity and understanding. Let's just focus on going through our program from X0 up to here, ensuring that each step is clear and precise. And let's say that all of them are 100 millimeter long, which is a standard measurement for our purposes. This length is chosen to maintain consistency and accuracy throughout the process. As I write my program, let's forget about G1 and G0, which are not necessary for this particular sequence, as they do not contribute to the current objectives, and go point to point. So X0, Z0, and I'm here, then X2, C2, because C gives me the chamfer, which is an important feature in our design, Z minus D, XB, C2, Z minus E, XC, R5. This approach allows us to maintain accuracy and efficiency in our programming process, ensuring that each step is executed correctly and efficiently. Minus stop. By varying these values, I can make a shorter piece, a piece with a larger diameter, a piece with a shorter E. So if I have a family of identical pieces, I can solve them all with a single program. For example, I did something really simple for a company that needs to work on bushings, like this with a through hole. They are all the same, all the same, all the same, but there are 400 of them. With one program and 4 variables, I standardized all the pieces that this company needs to make, while also standardizing all the feeds, all the speeds and all the rotations, without having to force the operator every time to think, what data did I have in the previous program? Up, down, left, right. Just one program, 5 variables, managing 400 codes. At this point, I would do a practical example on the simulator, assuming I have a brush. For making the grooves, let's take the piece we used. We'll slightly modify the little program we used for the sub-programs, and you'll see how simple it is. So let's remember that in the simulator and on iFanuc, the variables are not A, B, and C like on many CNCs, but are percentage 101 equals value, percentage 102 equals value. FANUC does not allow the possibility of writing X equals percentage 101 plus percentage 102. So if you have to add 2 variables, you create a new variable, such as, for example, percentage 104 equals percentage hash. This symbol is called hash. I apologize for the slip. Hash 101 plus hash 102, and then you will go to write X equals hash 104. Of course, just as you can use mathematical operations, you can also use logical operations, and we'll do a separate tutorial on that. So if hash 101 is greater than hash 102, skip the block. Tot, otherwise not. These are called logical operators. Today, we're limiting ourselves to looking at variables. We'll check them out on our simulator, where, as you can see, I've created a main program called Golem Multiple that considers a raw material with a diameter of 100 and a length of 100. I've set my initial data as always, determining 3 variables. Hash 101 equals 102, which is the outer diameter plus the safety distance. You see, diameter 100, I set hash 102 equal to 90, which is the bottom of the groove, and hash 103 equals 4, which is the groove width. Then I called the program 00100, shifting the origin by 15 millimeters. Now let's take a look at the program 00100 or 0100, and you can see that I've programmed it by telling it. I've set my initial data, as always, determining 3 variables. Hash 101 equals 102, which is the outer diameter plus the safety distance. You see, diameter 100, I set hash 102 equal to 90, which is the bottom of the groove, and hash 103 equals 4, which is the groove width. Then I called the program 100, shifting the origin by 15 millimeter. Now let's take a look at the program 100. 100, you see that I clearly programmed it by telling it 0x. Hashtag 101 is set to ZD10. Then I added another variable, which is hashtag 104 equal to 10 plus hashtag 103. Hashtag 103 was the width of my groove, which is 4 mm wide at the bottom. Then I put in the macro for the radial grooves that will go to X, hashtag 102, which is my groove bottom, and Z minus 104. What is 104? 10 plus the width of the groove. G0 returns to X 101. We call up the multiple grooves program and run it. G0 goes back to X101, which is the outer diameter of the groove plus the safety distance. Call the groove program and run it. I don't change the outer diameter, but I can change the groove bottom to 70. I can create deep grooves. Reset to 90, change groove width to 6 mm, height 46 for wider grooves. Enter subprogram, modify variable hashtag 102, the groove bottom diameter. Without even going into the subprogram, I can create nice, extremely deep grooves. Let's go back with the undo button, set my 90 back, and change the groove width to 6 meter and height to 46. And we'll see that we'll have wider grooves. You see? But let's do something even more interesting. Let's go into the subprogram, and at the end of my subprogram, we're going to modify a variable for hashtag 102, which is the groove bottom diameter. Now we're going to write that hashtag 102. At the end of the program, it ultimately and eventually becomes equal to itself. -10. We insert it. No, I shouldn't have done alter, but I should have done semicolon. What does this tell the machine? It reads the program, the subprogram. Once at the end, the subprogram modifies the value 102, which will go from 90 to 80. It runs it a second time, changing the value from 80 to 70. It runs it a third time, changing the value from 70 to 60. Let's see if what I'm saying turns into reality with the simulation. And you can see that the variables can be modified on the fly as we wish, using very simple math operations: subtraction, multiplication, and division. This is the first part about variables. Next video, unconditional jumps and logical operators. So greater than, less than, go, to jump, don't jump, make a choice rather than not making a choice, because a machine can make a choice based on a length. It can decide whether to cut the piece 10 times or 20 times if there's space. Obviously, if you've been clever enough to give the machine choices through math operations, it can navigate these decisions. I thank you. Practice a lot. Use your head and see if you can make the same choices that the machine would make. You need to create small programs using logical operators and arrows to choose where to go and how the machine will think and sketch out what you're doing. Don't just rely on the simulator. Also use a blank sheet of paper and a pencil to sketch out the tool's path yourself. You'll see that it helps. It's a bit more monotonous, it's a bit less nice, but helps. Thank you so much for being with me. I'll see you in the next video, I promise. Very interesting, and you'll see that I'll make some mistakes too, because sometimes it's hard. And Until next time, as always, if you like the video, share it on social media. Have a great day.